but it's really just how would we have done this problem? How would we have done this problem if we use the methods of Chapter 9? Okay? Just leave him. Alright, so let's do this again using the method of Chapter 9. So steps 1 through 7 are the same as before. So we get this input-output differential equation. So that Chapter 9 doesn't do any of that differently. It's just saying, how do we solve the differential equation? Let's use a method that takes into account the fact that first and second order systems come up a lot. Solving for these responses for first and second order systems can be done by putting them in a table and then using these properties like superposition to find solutions from the table. So we want to know what the step response of this is with initial conditions 0. So the first thing to do is to find the damping ratio. Okay? Natural frequency and damping ratio. So this is the standard form of the left-hand side of the equation. You might recall that I said that in the second order lecture. This is the standard form. It has second time derivative 2 zeta omega n plus omega n squared. And this implies that from looking at this left-hand side, that b over m is equal to 2 zeta omega n, right? And that omega n squared is equal to k over m. Therefore, I'll do the omega n one first because it's always the easiest. Omega n squared equals k over m, which implies that omega n is equal to, we're going to take the positive side, square root of k over m. So that was easy. 2 zeta omega n has to be equal to b over m, right? And if we solve for zeta, zeta is equal to b over 2 m omega n, which is equal to b over 2 m square root of m over k is what we got for our omega n. K over m. Can't remember these things today. I have my ratios wrong. K over m. And that is just equal to b over 2 root m k. It's a very pretty k. There we go. If we plug numbers in, then we're going to get 0.265. I plugged numbers in because I need to know what the damping ratio is before we can do the next part. Because if we look at the table 9.3, we have to know the damping ratio. So what do we know already? Because the damping ratio is 0.265. What do we know about the system? It is underdamped. Okay. So that means that the damping ratio is between what and what? 0 and 1. So it's also stable because why?
It goes back to 0.
Because it says positive, right? And that's, you're right, that is an implication of it being, yeah. So we know that it's stable because zeta is positive. So that's good. And if we look up this in the table, so I'll actually pull up the textbook. Table. Yeah, there we go. 9.3 has this in it, right? And we have damping ratio between 0 and 1, okay? And we have a unit step input. We're going to once again use superposition and all that, so we're going to just find a step response. And so it's equal to this. It's listed in the table. So we can write, I'm going to put this down here so I can read it off. Yes, you do. I will provide it for you. De nada. That was not related, Jordan. Okay, so our VMS of T is equal to, reading off the table, 1 over omega n squared times 1 minus e, so there's going to be this fraction, right? E to the minus zeta omega n t divided by root 1 minus zeta squared, all that times cosine omega d, which we haven't defined in this problem but is always defined in this table to be so where omega d is the, do you guys remember what this is called? It's the damped natural frequency, so it's close. So it's omega n times root 1 minus zeta squared. And the other term that we haven't defined is what psi is, which is the phase shift. Psi is defined as arctan of zeta divided by root 1 minus zeta squared. So those are our, so this is our VMS. So remember how we had to find the homogeneous solution, the particular solution, the general solution. We had to juggle everything around, with complex exponentials and all that stuff. We just wrote it down. That was really, really easy, right? Okay, superposition then comes in, and we say, okay, just like before, superposition and also the differentiation rule, which isn't technically superposition. We're just going to do the same exact step 11 that we did the last time, in the last lecture. So we did Vm is equal to K over M times Vms of T plus, wait. Well, yeah, I mean it is, but I don't know why I mixed them. Then I did plus B over M VMS dot, right? I don't know why I switched the sides. When I wrote this before, I wrote this with these two terms switched, but in any case, this is the same step. So if we go back to our other lecture, that was this 8-point-F step right here. So just do this step, and you'll find exactly the same solution this way. The last thing I'm going to leave you with is that on the website I also included a the same exact example in Mathematica. So I did it again in Mathematica, and I showed you how to use Mathematica to do a lot of these things. And I also I gave you a partial solution for this motor controller problem in your textbook, which is pretty cool. So you can check that out. And then here's a MATLAB script that you can use to play around with it. So a couple extra little things there at the end for you to play around with and studying. The final exam, as you know, open notes. I'll give you just those tables that are in the textbook, 9.1 and 9.2. Okay, those two tables you'll have. your the final exam, of course, is comprehensive, but it is going to be more focused on the last portion of the course because you haven't been tested over that material, right? So all of this system properties, second order stuff, finding the solution, finding your system transfer operator, being able to convert from state space to differential equation through the system transfer operator. That stuff will be more of a focus, but you can't do that stuff if you can't build a state space model and all that. So be prepared for anything and everything on the final exam. I think you guys will do absolutely great.